Welcome to ECEN 215 Principles of Electrical Engineering. Today we're going to talk about an introduction to Boolean algebra. This is in our topics on digital design. And so far we have led into with what is digital design while we're studying it, the different types of switching technology, how to go from a decimal number that we're used to, base 10 number like 1024, and convert it over into binary. And of course, in the various encoding techniques thereof, like ASCII or Unicoding. Now we're going to introduce some actual algebra that we're going to use to do this. So let's go ahead and jump into this and get started. So Boolean algebra and its relation to digital circuits. To better understand the benefits of the circuits that we're about to introduce, which are known as logic gates, and it's going to be in the following topic to this, which is kind of similar, analogous to the switching technology that we were just talking about earlier as well. So we're going to use this thing called logic gates, and they're going to implement logical functions. But first, we need to understand the concept of Boolean algebra. So first thing, it is, let's just talk about a traditional algebra, which you are very used to by this point in your engineering career and everything that you've gone through with prior to coming to Texas A&M. And obviously, traditional algebra, you represent variables as real numbers, x and y, for instance, z, and then you have operators that operate upon those variables and return real numbers. So you actually use real numbers, use variables that represent real numbers, and then there are operations upon those real numbers that will output as a part of a function real numbers. So that's traditional algebra. Boolean algebra also has variables, but they only represent 0 and 1. So instead of real numbers, just kind of let me highlight things here. So instead of real numbers, they're now representing only 0 and 1, which would make sense. We're talking about digital design. And of course, operators only are going to return a 0 and a 1 as well, instead of returning in traditional algebra real numbers. So again, that does make sense. That's kind of what we want with Boolean algebra, is we want to represent the true binary state of the functions we're looking at. And also, there are operators. Now, operators in the real traditional algebra, we have multiplication, we have addition, subtraction, and of course, division is our operators. Of course, there's exponents and a whole host of other things that we can do, parentheses, etc. But in Boolean algebra, we also have different algebra, but they're all logical based, like anding something, oring something, and notting something. What that refers to is A and B returns only 1 when both A and B are 1. In other words, A and B must both be a 1 to be itself valid. So in a truth table, and this is what a truth table is the different variables. Here we have A and B, and then we have the function itself, in this case and represents all the possibilities of A and B. We can have 0, 0, 0, 1, 1, 0, and 1, 1 are possibilities. In other words, we can have A both be 0 here for these two cases. In these two cases, it can be a 1. And then, of course, we have the possibilities of B. So A can be a 0 and 1. B can be a 0 and 1. Just a quick note, the number of rows, if you will, in a truth table is related to the number of inputs. So we have 2 inputs. So again, there's 2 possibilities, and the number of possible inputs here is 2 equals 4 rows. So if I had 3 inputs, I would end up with 8 rows, for instance. So again, for an AND, the only way that the f of AND, function f is equal to A and B occurs is when both of them are a 1. And of course, OR gate or ORs are the same way, function for OR, A and B. As long as one of the inputs is a 1, then it's going to occur. And of course, if both of them are 1, you always get a 1. The only time that it is 0 is if both inputs are a 0. And not is just the opposite of whatever the variable is. So if A is a 0, the not of A is a 1. And again, if A is 1, then the not of A is a 0. Fairly straightforward. So those are our different operators. So Boolean algebra was actually developed by George Boole in the mid-1800s to actually formalize human thought. And so again, the concept here that he was dealing with was how do you, for example, if I was going to formalize a phrase and actually have a method for writing that down in a more formalized format, what would that look like? So for example, the example we have here is I'll go to lunch if Mary or John goes and Sally does not go. So f is the function, is the outcome that we're desiring. So the fact that you're going to or not going to lunch is f. So if f is going to equal something, in this case, let f is going to represent us going to or my going to lunch. That is what's supposed to be. The I'll go part is the f part. And 1 means to go and 0 means don't go. So that is a formal way of doing that. Likewise, M is for Mary, going. In other words, if she's going to lunch, then M represents that. J is going to be used for John, and of course it's for going as well. And S is Sally going to lunch. So you end up with a function that is F is Mary or John going, which is what we have, Mary goes or John goes, and not to go if Sally does not go. In other words, not S. So I'll go to lunch as long as Mary or John goes and Sally does not go. So that ends up being this function here. So there's a lot of nice features of this. So we can actually formally evaluate all the possibilities here. We can write a truth table for all of this. And we can evaluate for different conditions. For instance, we can say Mary is going, John is not, and Sally is. We formally evaluate the function that we have, and we come out with, this case is 1 and 0. Therefore, since this condition is this case, so in other words, this right here is the 1, right there, and this, of course, represents a 0. Kind of poorly drawing this here. In fact, let me kind of clean this up a little bit here. So 1 and 0 here, it represents this part, and the not 1 represents this part, and so you end up with a result of 0. So therefore, you're not going to lunch. So it's very formal in its evaluation. Of course, we can transform this. We can change with using some properties that we're going to soon be talking about. You can actually transform this function to represent different things. You could say Mary and not S, or John and not S, or not Sally. So you can kind of change the function up, but in the end, it means the exact same thing. So of course, we're going to be talking about these transformation techniques soon enough. And of course, we can formally prove things. We can prove that if Sally goes to lunch, in other words, S is equal to 1, then I don't go. F is equal to 0, because you can run all the different possibilities of this. Again, in this case, how many possibilities do we have? We have M as an input, we have J as an input, and we have S as an input, Mary, John, and Sally, which means we have a total of 3. How many outcomes are there? There are 2 to the 3 possibilities, which means there are 8 possible outcomes. And so we could actually formalize this and actually create a truth table, which again looks like this, where you have these different functions. This is the and, the or, and the not. But you can actually write a truth table that has all the possible outcomes. And so therefore you can formally prove that, because we know that each input can only be a 0 and 1, and the output can only be a 0 and 1. So evaluating Boolean functions. So to evaluate it for a given variable, so again, here we have a function f is a and b or c and d. So we have values or variables of a, b, c, and d. So there are 4 variables for this given function. So again, just to kind of highlight, these are our properties or our operators. Again, we have the and operator, the or operator, and the not operator. There's a few others as well, but primarily in the sense of Boolean algebra, these are the ones that actually are the standard for Boolean algebra. You can create things like exclusive ORs and things like that, but you would make that out of these basic operators. So first question we have here, let's just go ahead and evaluate this. So we're going to use this function here, and we are now going to evaluate that. So we have a is equal to 1, we have b is equal to 1, c is equal to 1, and d is equal to 0. So if we write this out, we would have, I'm just going to write that over here, we have f is equal to a, which is 1, and b, which is 1, in parentheses, or we have C and D, which is 1 and 0. So immediately just following using these operators here, which you can pretty much already probably have committed ahead how these work. So 1 and 1, that evaluates to 1. And then we have 1 and 0 here. This, of course, everything's inside of parentheses, and since precedent, you do that first. So 1 and 0, this is 1 and 0. Both of these, and then this is ORed 1 or 0, so this immediately becomes a 1, and that's what we get. So let's continue on with question number 2. If we have A is 0, B 1, C is 0, and D 1, well, that kind of changes things. Now we're going to have 1 and 0, or 0 and 1. Well, both of the ands are both going to with that operator, going to become 0, and so our function will be 0. Question 3, we have everything as 1s, A, B, C, and D. So therefore, both of the ands and both of the conditions here are both going to end up being 1. So this will end up becoming a 1. This will end up becoming a 1. And since it's ORed, it all will become a 1. So therefore, we end up with f is equal to 1 and 1, or 1 and 1, therefore 1. So the f is equal to 1. So how do we convert into a Boolean equation given a particular phrase, for instance? So, and where these usually come from is if you're creating some different types of technology, someone's going to say, I need this system to generate, I need to turn on, let's say for instance, I need to turn on the air conditioner if the temperature increases above a number, and then I need to turn off the air conditioner if the number falls below a number. Just you kind of as an example, that's how you come up with the English phrase, is you look at the logical function that you're actually implementing. For instance, this happens a lot when you write programs and code. You have an if statement. This is where you're getting this converting over into a Boolean function. So let's start with one. So let's start with the fact that we have two variables, A and B, and we simply want to convert to an equation where A is 1 and B is 1. So in other words, we want the function to be 1 if A is 1 and B is 1. Well, that one's easy. That's just the and. F is equal to A and B. So question 2, we want F to be equal to, we want this to be true. Either A or B is 1. Well, again, using the operators we have, that's just simply an OR. F is equal to A or B. Now we want an output to be 1, in other words, turn something on, if A is 1 and B is 0. Now the key phrasing here, so this is an operator that we've seen before. We're having to now do a function. So we have the phrase and here, so that tells us one thing. But we also have B is equal to 0. So we need to combine things a little bit. So we have, in this case, F is equal to A and not B, so that we can actually use the and part, but we have to flip the invert B here. And then question 4, A is not 0. So there's a couple different ways we can go about that. One way is to say F is the not of A. In other words, it's just not 0, or just simply pushing through F is equal to A, because that, the not will cancel out this not, and then you end up with F is equal to A. So now that we've looked at that, so let's take a look at things basically different methods here. So similar to algebra, there are all sorts of different methods to manipulate these. In the end, these are actually going to be circuits that we're going to create. But first, we're just going to manipulate the algebra here. So right now, we've been writing things in actually kind of a long form. We're actually been saying A and B, or A or B, not A. Well, if you have a complicated function, this can get a little cumbersome, for lack of a phrase. In other words, you end up with this very long sentence describing something that's very easy to make a mistake. So instead, we're going to use different symbols, and of course, we're going to represent the variables in a similar fashion, but we're going to use some different symbols. So we're going to use symbols. We're going to use the asterisk or the multiplication. We're going to use this, A dot B, or just simply AB, just like we would basically say A times B. We're kind of representing, I'm using air quotes here, multiplication to represent the AND function. Now, it's very important to note, this is not multiplication, okay? Because you're not multiplying. So like if A is equal to 1 and B is equal to 0, make sure you're not doing AB is equal to 1 times 0 and equals 0. This is not how this works. This is, in the end, this is representing AND. This represents AND. And this represents AND. So that's the key thing here. And of course here, A plus B, this represents OR. And the product symbol, this is not A plus B. Not that. So like again, if this A is equal to 1 and B is equal to 1, this is not A plus B equal to 2. That is not what we're doing. This is simply representing the function OR. We're just using the symbols that we're used to seeing historically in the past for algebraic manipulation to help make it cleaner, basically a cleaner way of writing an equation. And the same thing with basically using a little apostrophe here, or using a little line above the letter representing not. So this represents not A right here, or this as well. And this is very common, going back and forth between the two. So here, like for instance, let's start here with an original function, W. Instead of F, we're going to use W. So the variable W is going to be P and not S and K or T. So this is kind of, quite frankly, a little hard to read. So it's a lot of letters here, and when I'm looking at this, my brain's kind of jumbling up. So let's just go ahead and rewrite this, and we end up with P, S not K. So that's the P and not S and K. So again, we're converting this parts into just different nomenclature. In this case, we're just doing P, S, there's your not. This, of course, is all being multiplied together. Multiplied, in other words, being ANDed. Let me actually kind of use the right words. So we're taking the product, as it's known as, of A and not S and K, and we end up with this part representing all of this. And then it's OR T, which is where we have the plus sign here, T. So this part is this right here. So we speak it as W equals P and S prime and K, or T, where S prime is the complement or the inverse, not of S. So we can also, while symbols, so we don't say again times or plus, even though I was kind of using that before, just to kind of get you used to seeing what this means. This is really the product and the sum, and then they are okay and are commonly used. So again, this is the product term, and this, again, this total part here, this already pre-done, done precedence first, becomes the product term of PS prime K, product of T, not plus. This is not plus, and this is not multiply. This is dealing with, again, ANDing and ORing, or the not. So what we have here, just algebra precedence, the highest precedence first. So again, similar to standard algebra, parentheses always takes precedent. You figure out what is inside the parentheses first. Then you do the not function next. So you inverse everything. And of course, you're evaluating everything from left to right. And then you perform anything that needs to be ANDed or the product terms next. And then finally, you evaluate your or your sum terms next. So that's how that's done. So let's go ahead and practice a little bit here on this precedence. So we have a function here, f asterisk b plus c. And we have, of course, our variables that are provided in their actual a, b, and c, and d. So we just need to plug these in and evaluate this function. So the first thing we see is a asterisk b, which is, again, in the sense of precedent, we're needing to do the anding first. We don't have parentheses and we don't have a not, so the next one precedence is the and. So a and b is equal to 1 because we have a and b are 1. And then it's going to be ORed with c, so 1 or c, which in this case is 0. This ends up being 1. So written out, we simply get, again, the asterisk here, the product term has precedent over the sum term, and so we evaluate it as such. Next, we have AB summed with C, which this ends up being, in this case, this exact same thing. The only thing that's changed is we got rid of the asterisk symbol and we just replaced it with AB. So it's exactly the same function. There is no difference between this function and this function, just the way it's written. So therefore, it evaluates the exact same way. Now for problem 3 here, we have f, a, b, naught. So we have this, which means what? This means this is actually a and not b. So you evaluate this part first, and then you do the anding, which in this case is 1 and the not b is a 0, which ends up being 0. And that ends up that value. Now we have for the final, or for number 4, here's actually, there is one more, there's a number 5. We have f is equal to AC inside the parentheses here. So we have parentheses, and then that is not. So what this means is first you evaluate A and C, which in this case, A is 1, C is 0. So this represents 0. Then you take this, then you're going to apply the not on it. Because remember, first thing is parentheses, then not. So that ends up being A and C, which is 0, not that. So this evaluates to 1. And for the final one here, we have a little bit more of a complicated function. We have A plus, or sum, not B, ANDed with C, ORed with D naught. So first thing we can do, take everything individually in order of precedence. Well, the first thing is looking inside. We have to do what's inside the parentheses first. So that number 1 is this. Then number 2 is the nodding. And then 3 is the anding. And 4 is the ORing. So we're going to go in order. We're going to do what's inside parentheses first, which is A ORed with B naught. Well, we need to do the not first. So this ends up being A plus, in this case, B is 1. So we end up, let me erase this here. We're just going to write it out in the value. So that's 1 plus, and I like to say plus, even though it kind of discourages this, even though this is a sum term. I say plus, even though I know this is a OR term. Not B. B is 1. So therefore, this becomes 0. But it's an OR, so therefore this becomes 1. So that's that. So let me go ahead and write that down. So we end up with this as a 1, and then we're doing and C because of this right here. So we have 1, and C. C is a 0, so that's that. So all of this part here is equal to 0. So now we have 0 plus D naught. So what does this evaluate to? Well, first, again, in order of precedence, we need to do the not D first. Well, D is a 1, so we end up with 0, our first part here, plus 0, which this is equal to 0 or 0, which is equal to 0. It's kind of written out here what we've done here. Okay. So now that we've looked at that, let's kind of expand some terminology here. So some Boolean algebra terminology. We have an equation here. We have our function, which is a function of a, b, and c. And of course, it has all of these terms in it. So first of all, there are the variables. Well, there are only, in this case, 3 variables. The 3 variables are a, b, and c. Now, but they're used in multiple times in different forms. But the actual variables, and they represent a 0, 1, are a, b, and c. Then there are the literals. The literal is every appearance of the variable, and it's either it's true or complemented, or are also known as not or inverted form. So in this case, there are 9 literals because we have 1 here, we have number 2 here, 3 here, 4, 5, 6, 7, 8, and 9. We have 9 literal terms. Now they're all the same variables, a, b, c, but they're actually evaluated here. So we have a prime, b, c, d, b, a c prime, a, b, and c. Then there are the product terms. Here we have this as a product term, we have this as a product term, and we have this as a product term. Technically, you might be able to say this is a product term and that it's c ANDed with 1, but reality there's only 3. Well, yeah, there are 4 product terms. It even says here 4 product terms because it's c, ANDed with itself. So there's product terms are this. Because remember, the product happens before the sum. So the idea is you do the negation, you come up with all your literals, and then you focus on your product terms, and then you have what's known as the sum of products. Because now we have our product terms, and then we sum them or them together. So there are 4 product terms, which means we have product term. Let's just call this, let's see, M, N, O, and P, just to pick some letters. We have M or N or O or P is equal to F, A, B, C. So that's the idea there. So this equation is known to be in sum of products form because of that. And of course, this equation right here is not in that form. And the reason for that is because we have a product term here, and then we have it combined with an and term here. So this is not effective sum of products form. But this is still Boolean algebra. It's usually in general, it is in general good form in digital design if you're dealing with Boolean algebra to get your final equation in a sum of products form. So now we're going to talk about some Boolean algebra properties. So similar to properties you have with traditional algebra, there are properties with Boolean algebra, and they're a little bit similar to what you're used to with traditional algebra. So commutative, meaning that A or B is the same as B or A and B is equal to B and A, which is logical and makes sense. You have distributive, meaning that you can take the A and B or C and just go ahead and distribute the A into this. So you have A and B or A and C. Of course, you can rewrite this in a little bit simpler term. Then you can also do the A or B and C. You can represent as A or B and A and C. This one's tricky. Here's the proof if you want to see it. There is associative in that you can distribute everything around here, A or B or C. Because you have the parentheses, it doesn't matter. You can just rewrite it like that. And the same thing with the ANDing. Since these are all being ANDed together, it doesn't matter where the parentheses lie in this case. Identity has to do with just simply it's coming across a 0 or 1. So 0 or A is the same as A or 0, which is simply A. And of course, A ANDed with a 1 is always equal to A. And then the complement just deals with the fact that if you're complementing, if you have A and you complement it against the inverse of yourself, it's always going to be equal to 1 because one of these statements are always going to be a 1. So if A is equal to 1, not A is always equal to 0. But if you're ORing, it's always going to be 1 because one of these is always going to be true. And the same thing here. If you AND yourself, the not version of yourself, it will always evaluate to a 0. And this, of course, is you can prove all these by just evaluating all the possibilities of this, which is fairly easy to do. So, and there's just some, So what about a complement of a function? So we have a function f, and sometimes we actually want to find the inverse of that function. In other words, if f is 1, we want the inverse, we want the 0, basically. Sometimes this is really useful. Sometimes it's in fact when you actually go into reducing logic. In this class, we're not going to get into that, but if this was truly a digital design course, one of the things that happens a lot is simplifying your logic. Sometimes you can get a really complicated function for f, but sometimes it's easy to find the inverse of f, and sometimes the inverse function is actually simpler. And then again, all you have to do is invert it. Put a not on the end of it. Boom, you got your original function, but it's a simpler version. So if you want to find the inverse of a function, there is a way of doing that. This is known as De Morgan's law, and is defined on something of more than 2 variables, where we have A, B, and C here. And if we want to know the function, so here for this one here, f is equal to A plus B plus C. That's our function, and we want to get f prime. In other words, we want not f. And so that's our goal. And so if you do this, what you do is you do A plus B not and C, and you take the not of that. All you end up doing is just taking the inverse of the variables, A prime, B prime, C prime, and instead of what you're doing is you're distributing the not inside to all the variables, and then replacing the sum terms now with ands. So you do that, and that's how you do this. And of course, the inverse is true if you end up with A, B, and C. First step is to take the inverse inside. So you end up with A, B, A prime, B prime, C prime, and now convert the sums, or not, excuse me, the product terms with the sum terms, and now we end up with this. So again, just kind of review. We have A, B, C, or A plus B plus C is our function f, and we want f prime. And so what we do is first we convert it over to A prime, B prime, C prime, and we replace the plus signs here, the sum terms, with the and terms, the product terms. So that's how we get that. And then if we have here where f is equal to A, B, C, then what we need to do next, and we want f prime of that, we end up with first doing the inverse of the variables. So now A prime, B prime, C prime, and since they were all multiplication in the first place, now we're going to come back with the summation terms. So let's take a look at this function. So let's say we want the complement of f, which is w naught xy summed with w, x prime, y prime, z prime. So sometimes I say not, sometimes I say prime. So w prime x, y plus w, x prime, y prime, z prime. So what would we do here? So first step is we want f prime. So we'll just go ahead and write that out. So f prime is just the prime of this entire thing. So we know that. So again, we're going to focus on taking and distributing this prime inside to all of the variables. And then of course, then we're going to focus on changing all of the ands to ors and then all of the ors to ands. So let's do that. So first step by De Morgan's law is we're going to go ahead and convert first these two little subparts. So remember, see, we have that right there needs to become an and. So that we're going to do here. And then we're going to, of course, we're going to keep those primed. So we're just going to focus on this part first and then this part. And so we do that. Notice we haven't flipped the variables yet. It's still w, x prime, y prime, z, w prime, x, y. The only thing we've done is focused on this. We're kind of taking this thing backwards. We're starting with the or first and then working backwards. So next we have that. Now we go ahead and distribute in the inverse. And so now remember that these were anded, so now they become ors. And also we have the w prime becoming a w, the x now becoming x prime, the y becoming y prime, the w here became a y prime, or a w prime, x prime became x, y prime became y, and z prime became z. Now we can expand this into a sum of products form, because right now this is not in sum of products. So we kind of want sum of products. So what can we use? We can use distributive, and we can expand this, and we end up with this. So this is our original f prime. We distribute, and it becomes this ugly mess. Because what you're doing is just like with regular algebra, so you should be used to this by now and with algebra, but it's the same property. Take the w and multiply it through, and we end up with that, and we take that and we multiply here, we take the w, multiply by here, we take the w and we multiply by here, and then the same thing with the x prime, this and this, and of course we distribute the y inside as well. We have y going here, y going here, y going here, and then y going here. So you end up with this long function. But what can we say about this? Well, we know this. We have these terms here. W prime, we have x prime x, and we have y prime y. So this is interesting because what are these? These are equal to zeros. Why? Because that's one of the properties we have. So we complement out and we end up with this. It's a more complicated function, but the nice thing about this is that we're going to see in the upcoming lecture, we can actually convert this over to logic gates. So in summary, we looked at the introduction of Boolean algebra and how to actually represent a line of thought formally into an equation with variables and then literals. And of course, we looked at the precedence and properties of Boolean algebra, which is a little bit like traditional algebra, but there was some caveats. And then we also looked at how to take a complement using De Morgan's theorem on how to take a complement of a Boolean function.